Hello there, Math 126 students. Somebody's asking me about this fall 2021 question. It's sort of like a multiple choice question. I just made a video giving advice of how to approach multiple choice questions, but let me recap. So for things like this, it's kind of these three steps. Step one, can you prove it? Meaning, what are facts? These are things you can always do to help you think through such a problem. Write down any appropriate facts and formulas. For example, A dot A, what can we say about that? I mean, there are several things we should know right away. It gets the magnitude square, but let's say we forgot and we only could remember the one 10-star fact. Well, the angle between these two vectors, well, I'm just writing down because I don't want to say anything else. Similarly, let's just grab some other ones. What are other facts and formulas? I'm not even trying to think about whether what I'm writing and what it says is true or false. I'm just writing down every fact that we know about these. This should be... See, I find that students sometimes have this feeling of, if I don't know how to see it right away, I can't do it. It's not like that. I am not going to allow myself to even try to be confused until I do this. What are other facts? So let's just play a fact-finding mission. What is the most important thing about these various pieces? The cross product of two vectors. Well, that vector is going to be perpendicular to both. This is just something you could do in doing these problems. And I think the other two parts have to do with projection. We can get to that as well. So that's part of your repertoire. You don't have to just look at what's there. You can also bring with you the things we know. Step two, try to disprove it. So first you try to prove it. You say, does it immediately follow from something we know? And that might answer the question right away. Then you try to disprove it by coming up with counterexamples. This is a general approach to essentially any mathematical statement. It's a big part of what math is once you get beyond these entry-level courses, is we're either trying to prove something or try to disprove it. I really like to emphasize that because sometimes I find when students do examples, they tend to make up examples where it's true. Your goal in making up examples is to try to come up with something when it's false. Okay, lastly, if all else fails, then we're going to label unknowns. Like label it A1, A2, A through whatever. And we're going to try small examples. So that is your strategy. Now I know that does not give a clear ending time for the problem. And that makes it sort of scary for students. They're like, well, what if we take it forever? Yes, that's a bad part about multiple choice, is you may like fly through 2 or 3 of the parts and then be stuck on 2 or 3. I think for a final exam, that's more appropriate because you have more time to come back and think on it. So what I would do is do what I'm doing now. Okay, so now let's read the question. It says, suppose that A and B are non-zero vectors. As we read these questions, we should definitely make note. So that's saying that there are not 0, 0, 0. There are 3D vectors, but they're not 0, 0, 0. Decide whether each of the following is always true, sometimes true, or never true. Okay. If your answer is always, briefly explain why. If it is sometimes, give an example. Okay. So, the first one. Well, if you have the same vector dotted with itself, this actually was a fact we used a few times, that this is the same as this squared. And you might say, where did the cosine go? But if you're talking about the same vector, the angle between them is 0. Now, the only catch is you might say, well, couldn't it be 0? No, because they're non-zero vectors. So yes, this is always bigger than 0. This is an immediate consequence. Now, let's say you were unsure when you were doing this. You could skip to trying to come up with examples or counterexamples, meaning just try like 1, 2, 3, see what happens. Or try 0, 0, -1, even smaller. By then you'll know the answer as well. So I just like to say that, yes, these can feel daunting, and I know why students are worried about them, but you do have a fail-safe, which is you can try a bunch of things. So you just have to change your mentality in approaching these problems. Okay, next one. So writing down general facts, there's not much I can say. I mean, I can say that this is in the same direction as A. So same direction. I can't really use any formulas. We don't have, I would, collect everything we know. Same direction as A, but twice as long. So why can we, so again, if we can't reason it out from what's there, we could set it aside and try to do some examples later. Do small examples where the cross product is easy to do. But honestly, if I think about what it just said, I have two vectors A and B. I take their cross product. It's going to be perpendicular to both of them. If I think about what 2A is, it's going to point this way. So the question is saying, can these be the same? They cannot. How? Yeah, I'm just trying to think of if there's no way. So they can never be the same because they don't point the same way. It is always hard to think about, am I missing some small example? So like if I was still unsure here, I could make a note at the end of the exam to come back and play the labeling game, meaning do some small examples. All right, let's keep going. Again, the first step when I see this is I would write down these formulas. And I would say, okay, I've got this, and that means these are the same. But hold on, that would mean that sine and cosine are the same. So now I have to think, are sine and cosine always the same? No. Are they never the same? No. Sometimes sine and cosine are the same. When the angle is pi over 4, or when the angle is 5 pi over 4. So the answer is sometimes. So that one I didn't have to think very hard, but you can see it would have been really hard if I hadn't followed step 1, which is to write down any related facts or formulas. Okay, so then we get to projection. So let's review projection. So there's a couple things about projections. We have a formula, which is B dot A over the magnitude of A. And we have this formula, B dot A. You can either write it as the magnitude of A squared or as A dot A times A. That's the formulas. And those would be on your note sheet. And then we have the magnitude of B. So I haven't tried to let myself think about the problem yet. I'm intentionally just writing down the facts. I would have a visual to go with this, which is we have this vector B. We're projecting it onto A. And every time I wrote the projection formula, we had this little visual. We're going to go straight down. A is the ground, is how I like to say it. The ground is on the bottom, which makes it easy to remember the formula. The ground is what's here. We think of it like the base of what we're doing. That right there, there's two things we've said about this now a few times. This length is what this is. The vector itself is what the projection is. So the reason I'm saying that is often in like a true false multiple choice question, you might be able to finish I'm hoping that I can answer the question right away just based off of looking at these pictures. Now, if you understand the idea is you don't even need to draw the picture, but I'm just making a note. Okay, so I have those formulas over there, and I have the pictures of what they are. All right, now I'm ready to read the question. So the question says, can the component projection, this dot product, this length, be greater than the length of B? Now the length of B is from there to there. The length of B is the length of the hypotenuse of a triangle. The length of the hypotenuse can't be smaller than the length of the other side, so it's never. So I was able to argue that geometrically. Again, if we didn't see that, we would run a bunch of small examples, and you would find out after several examples that it's not happening. That would at least rule out always. So that is, like I said, the scary thing is time. But in the final, you do have more time. So if you have this in the back of your mind is you're going to write down the facts and formulas. You are going to see if you can deduce from that. If not, you're going to run some examples. And if you feel like that's going to take too long, then you go on to other things and come back. And on the final, you have a lot of time. So at the end, you could think more carefully. Some instructors like these more than others because, it's a way to ask maybe a harder question that isn't worth that much. That's conceptual. All right, let's do the last one. So the last one says, the projection of B onto A equals B. Now that feels really weird to me because why would these be equal? And so that, to me, this is the challenge of, it feels like it should be never. But could I draw anything unusual to make this happen? Well, what if the vector was right on top of the other one? Then B and V would be the same. That's a weird example, but I don't think it says they have to point in different directions. Part of the reason I can do this quickly is because I'm used to trying to think up examples. Now, I actually already thought about this up here. What if they point the same way? But in that case, the length of B would have been equal to the L. And since it was strictly greater than, it was never possible. If it was greater than or equal to, it could have been. So I think this can happen if B is in the same direction as A. So sometimes. So again, that was a challenge, but I hope I at least gave you strategies. What are your facts and formulas? Can you come up with counterexamples, label unknowns, try small examples? I mean, I was able to do the whole thing without trying small examples. Let me know if I made a mistake in my logic. I didn't check it, but I just wanted to give you a way to think through the problems. All right.